Hello, hi. So I'm just going to go through a few concepts relating to vector spaces. I know in the last video I sort of gave a definition. That's important, but really the way they're used is really important. So we can see the topics here. We're going to look at independence of two vectors, and then we'll have orthogonality of two vectors, and we'll discuss the difference between those two. Then what is the concept of a span of a vector? What does it mean for vectors to span an area? And then basis vectors and Gram-Schmidt orthonormalization process. Okay, so independence of two vectors. If I draw one vector and I draw another vector, clearly this vector is dependent on this vector. It can be written in terms of this vector. In other words, if I take vector A and I shrink it and reduce its direction, that gives me vector B. These vectors are dependent on each other. On the other hand, if I start with a vector and then I have another vector, there is nothing that I can do, no linear transformation, no linear, multiple I can take of A, which will turn it into B, right? Of course, obviously I could rotate it, but that's not the point. I can't scale it with a real number and turn it into B. I can't shrink it or reverse it and turn it into B. I can't add it to itself and make it into B. So, a set of vectors, let's call it A1 up to AN. There can be as many of these as we want. A set of vectors is linearly independent if the equation C1A1 plus as many as we want up to n. So C is the coefficient. That's a real number, for instance, just an element of a field. If this general linear combination of all the vectors from A1 to AN, if the only way to zero that out is to say that all of the coefficients are equal, they're all zero. In other words, if we have a trivial solution, then the set is independent. If we have at least one, any of these coefficients being non-zero, then it's a set of dependent vectors. And the reason for that is if these vectors are able to algebraically zero each other out, then in some sense we could rearrange it and write one vector in terms of the other vectors. So there's independence there, and then there's orthogonality. Now, orthogonality is sort of a stricter sense of independence because, this is orthogonal, right? So B is orthogonal to A in this case. Because what do we have? We have the dot product or the inner product. So actually I like to use these angle brackets to represent the dot product. If it's 0, then these vectors are, if it's 0 and neither of these are the 0 vector, then these two vectors are independent of each other, orthogonal of each other. Now, the difference between independence and orthogonality. Independence does not necessarily imply orthogonality. On the other hand, orthogonality does imply independence, because clearly, from this simple example, we can see that these two vectors do not depend on each other. And here, we can see that these vectors don't fully depend on each other, but there's some component of B which is in A. And that actually sort of brings me to another point. When we compare two vectors, there's sort of a fundamental decomposition result. Let's call this vector B. Let's call this vector A. I can do the vector projection down onto A, and that gives me some component of B, which is parallel to A, and then there will also be some component of B, which is orthogonal to A. And the vector sum of these two reconstructs the original B. So every vector, when we compare it to another vector, breaks down into two parts. A part which is parallel and a part which is perpendicular or orthogonal. So this is straying a little bit, but I do think it's important just in life. For instance, if we're trying to represent some higher dimensional function in a lower dimensional function space, then we want to minimize the error. In other words, we want the only difference between the real result and the approximate result, we want the only difference to be orthogonal, because that minimizes the length. So we think of this as like the error length. Anyway, I've gone a bit far on that. But okay, reel it back in. Span of a vector. So it's pretty common to say, okay, if I look at two-dimensional space, that's a bad drawing. If I look at two-dimensional space, then I sort of have two basis vectors. I have my x vector or my I, my y vector or my j, if you like that. So again, the standard vectors here are I and j, but they're really sort of synonymous with the x and y directions. That's fine. And then I say, okay, well, this I and j, this x and y, span out R2. They span out the two-dimensional real number space. So if I have any point, I can always get there by some combination of I and j. So in other words, let's call this, who knows, let's just call this z, doesn't matter. We'll say z is some multiple of I plus some multiple of j. And so if we have a set of vectors v, so I'll say v be a set, I is, for simplicity, we'll just go with indexing them with natural numbers. We could have like arbitrary families of sets, but I'm not going to go into that. This is simple enough, especially for just three-dimensional space. Anyway, so I'm getting off the point. Let V be a set of vectors. Then we have the span of V is a set. We'll call this U, where U is a linear combination of coefficient times the vector. In other words, the span is a set of all possible linear combinations that we can make with the elements of the vector set. So if we just look at the two-dimensional example, then any point here in this 2D plane is some multiple of I plus some multiple of j. And so the span of I and j is the 2D space. So where was I going? Lost my train of thought. Span basis vectors. Okay, basis vectors. So let's say that beta is a set of vectors of any size. It can be two-dimensional, three-dimensional, 10-dimensional. It's fine. We say beta is a basis for a vector space V. Yeah, so beta is linearly independent, and then the span of beta gives us the vector space V. So this should sort of make sense, but this is the mathematically pure definition. So Let's look at two-dimensional space, for instance. Clearly, I and j are independent of each other, and any combination of I and j can give us the full two-dimensional space. But they don't have to be orthogonal, they can just be linearly independent. So let's take I, let's rotate j a little bit so it does have some dependence on I, but still, these two vectors are linearly independent, and if I add combinations of them to each other, I will still get the full space. Now, as another example, if I have my I, j sort of system here, and then I add another vector, which is, it's redundant, right? So this would not be a basis for R2 because of a triviality. We would just remove this vector and then we would have a basis. Okay, fair enough. But on the other hand, this vector space cannot be a basis for R3 because although the vectors are linearly independent, if I add any combination of them to each other, I'm never going to get another dimension, right? I'm never going to be able to fill all of the three-dimensional space. Anyway, so this kind of gets us to the final topic that I want to go through, which is Gram-Schmidt orthonormalization. So if you're given a set of vectors like this, we can sort of reduce them to an orthonormal basis. Now we could do this one, or if we take this vector as our first one, it could be something like that. Orthonormal basis. The point of an orthonormal basis is the two vectors are orthogonal to each other, so they're perpendicular to each other, and they're normalized, so they, maybe not that, but they should have a length of 1, both of them. So Gram-Schmidt orthonormalization, how does it work? Well, we throw in a whole set of vectors, and then the result is an orthonormal basis. So we say, as a matter of fact, I'm going to do this by example. It'll probably make the most sense. Okay, so there we have it, 3 vectors. Now, just to show you, I'll briefly plot these 3 vectors. So we're looking in 3-dimensional space. So here's our A1. And then our A2 is 1 in the X and 1 in the Z. And then our A3 is 1 in the Y and 1 in the Z. Something like that. It's a little hard to see, so I'll just drop these lines down so we see that lines up with the X-axis, that lines up with the Y-axis, and this is in the XY plane. Now we need to take these 3 vectors and produce a orthonormal set of 3 orthonormal basis vectors. So what we do is, first of all, let me put B for my basis. I'm just going to throw in A1. So I just pick the first vector and I throw it into my vector space, and I say, throw it into my basis set, and I say, there you are, you're the first basis vector. But I'm not just going to throw it in, I'm also going to normalize it. So I'm going to say, okay, the magnitude here is 1 squared plus 1 squared, which is square root 2. Okay, so as I throw it in, I normalize it. So I go, okay, 1 over root 2, 1 over root 2, 0. Okay, that's the only vector that I have in there. Now, for my next step, I want to take A2 and I want to throw it into my set as well. But A2 could have some component of it which is parallel with A1. So what we want to do is we want to say, okay, the component of A2, which is parallel to A1, will be the projection of A2 onto A1. So in other words, that is, if we take the product of A2 and the normalized A1, and then multiply it by the normalized A1. So we have the normalized A1 here. We can look in, we have, okay, so we go component-wise, 1 times 1 on root 2, plus 0 times 1 on root 2, plus 1 times 0, so it's just that, times A1, which is that, and this comes out to, well, 1 on root 2 times 1 on root 2 is really 1 over root 2 squared, so that's 1/2. Okay, so this vector is the part of A2 which is parallel with A1. So in order to get the parallelness removed, we simply subtract it. So we say, okay, we know that A2 is the part of A2 parallel with A1 plus the part of A2 perpendicular to A1. And so to get the bit that's perpendicular, which is what we need to put in the basis set, we will take A2 and remove the parallel part. Okay, so then we just subtract this away. So we have 1/2, negative 1/2, 1. Okay, then we need to normalize this. So we say, okay, just square each of the components. So 1/2 squared is 4. This is square root of 1.5. Then we go ahead and divide by this. We multiply by root 2 on 3. So just did a bit of simplification there. If we have 1 on 2 times root 2 on 3, then of course that comes out to 1 on root 2 times 1 on root 3, which is 1 on root 6. Okay, so this example is getting a bit big, but let's keep going. So the point is, we had this one on this this vector here. Was our first basis vector. Then when we threw in the next basis vector, we made sure none of it was parallel with anything that was already in the set. And there we have it. That's our set. Now we throw in the third vector, which is 0, 1, 1. Okay, so I'm going to kind of speed run this a little bit, but what we need to do is we need to remove the parallelness with any existing vectors. Okay, now we'll just work out this coefficient here. So as you can see, the dot product is indicating what proportion of the vector is parallel with the basis vector, and then we're removing that proportion. Right, so this turns out to be 1 on root 6, and that's good because as we multiply that in here, these numbers are going to simplify. So we get righty, so then we just do the math. So we have, what is this? Hopefully I've done that right. Okay, so then this is our third basis vector, but we need to normalize it. So then we find its norm, which is, oh, turns out to 1. Wait, does it? Am I going crazy? 8/9 plus 9/9. That's definitely not 1. Something like that. Okay. Something like that. Yeah, okay. So, a little messy in the end there, but that is the full orthonormalization process. Again, we have a set of vectors, and then I like to think B like basis, B like bin, beta like bin. So what I do is I would throw them in the bin one at a time, but as I throw them in the bin, I only throw the new stuff, right? So when I throw it in, I remove any correspondence with existing elements in the bin. Okay. So anyway, hopefully that's helpful. Hopefully that's taught you some stuff about basis vectors. And yeah, I'll see you in the next one. Bye.